Hello, my name is Damian Perez. I am a paleontologist from Argentina, living today in Puerto Madryn, in Patagonia. I am working in the CONICET, at the Instituto Patagónico de Geología y Paleontología. My work is with the research group NEOMAP, Neocean Marine of Patagonia. And English is not my native language, sorry for it. And sorry for my English. My main research interest is the family Carditidae. This family is the objective of this talk, and my objective is view some approaches applied to this group and learn about them, and think how this could be extended to other groups. Here in this plate are the bivalves. They are beautiful or not. The bivalves are one of the most conspicuous group of animals because their shells. There are a lot of bivalve shells, different bivalve shells. These shells come in a wide range of shapes and colors today, as we can see in this plates. This one from Haeckel, more than 100 years ago, and this one from Sedler, more recent. Among bivalves, we have the clamshells, the cuckoos, the giant cuckoos like Tridagna, the giant, the most large bivalve, and the scallops, razor clams, mussels, oysters, nutshells, arc shells, angel wings, etc., etc. Here a summary of different phylogenetic schemes for bivalves from the last 40 years, and with the emergence of new methodologies for phylogenetic research, the knowledge about the bivalve relationships was increasing. Some years ago, since 2002, a new group emerges, named as the Archiheterodonta. This is from the works of Hiribet and Wheeler, mainly Hiribet and Distel and Hiribet in 2008. This clade is based on several data sources, mainly molecular ones, and posterior analysis agree with the monophyly of the Archiheterodonta. So this is a very recent phylogenetic tree of all bivalves from González Dole. We can show the Heterodonta. They are the Archiheterodonta. The Heterodonta is the most successful living group of bivalves, more than 800 or more species of bivalves. They split in two recognized groups, separate one from the others: the Euheterodonta or true Heterodonta and the Archiheterodonta. The Archiheterodonta, the main focus in this moment, or also called as primitive heterodonts. I don't really like the word primitive, but it's used. The Archiheterodonta are all marine bivalves, and they have no siphons. In reverse, the Euheterodonta generally have siphons. The Archiheterodonta includes many fossils previously known Actinodonta and other groups. For example, the Eurycrestaloia, the Eudonidae, Archiheterodonta, Carditidae, etc., etc. And the living Carditoia and Crestaloia. But there are no morphological definition for the Archiheterodonta. Today, Archiheterodonta are composed by two big groups: the Crestaloia, composed by the Astartidae, the Crestalidae, and the Carditoia, composed by the Carditidae and the Condylocardidae. These four families are some of the most neglected bivalve families, the less researched, the less studied families of bivalves. The Condylocardidae, for example, have extremely tiny shells, under 1 centimeter of length. They are very poorly known. If you pay attention, the Condylocardidae arose from the Carditidae in this phylogeny. But the focus of this talk are the Carditidae. Because the Archiheterodonta is based on molecular data, there are no morphological synapomorphisms proposed for this group until today. Well, how will we go with the Carditidae? Finally, they are beautiful bivalves, mainly characterized by the radial ribs. This is the most conspicuous character when you look at the Carditids. And among internal characters, they have 3 cardinal teeth in the right valve and 2 in the left valve. They have no scutcheon, they have a lunule, etc., etc. But the main question to guide this talk is this one: what do we know so far about the Carditidae? The first question. And for example, their fossil records. What their fossil record begins. The fossil record of the Carditidae begins in Devonian, maybe. This is Carditomantia, and from the early Devonian of Svalbard, North Seas, Arctic Sea. This was proposed as the Moose-Asian Carditid by Chaban in 1969, but this is not a Carditid according to posterior authors. Carditomantia has the radial ribs, but maybe it's the only Carditid character, the radial ribs, present in Carditomantia. So we have also the Palaeocarditinae. The Palaeocarditinae was a subfamily proposed by Chaban, also in 1969, to group all pre-Cretaceous Carditids, known until this year. The Palaeocarditinae, like Palaeocardita crenata, are from the late Triassic, early Jurassic. There are some genera like Palaeocardita, Septocardia, or Schizocardita, and other like Pseudopis and Trocheria. But some of these genera are considered today as Astartids, and the relationships between Palaeocarditinae and the remaining Carditids was very discussed by several authors. mainly because the character presented by the Palaeocarditinae. For example, the escutcheon I mentioned before. The escutcheon is present, is well developed in the Palaeocarditinae, but is absent in all other carditids. But the radial sculpture is present too. Let's go to the Cretaceous. Here the picture looks much better. We have some taxa more carditid in essence. For example, Xenocardida from the Early Cretaceous of Lebanon, Cretocardia and Venericardia from Late Cretaceous, Paleocene of North Africa, India, Mozambique, North America, or Birkelundita from the Late Cretaceous of Netherlands, Belgium. There are many more. Here some names, and maybe we have a much better picture of the Cretaceous carditids. So we can consider the fossil records of the carditids begins at least as early Cretaceous, and for sure it comes to the present day. They reach recent times. We have carditid in our beaches, in our shores. These are carditid pictures, pictures of living carditids. The carditids are living today. In other ways, the carditids are divided in two main groups based on reproductive characters. This classification from Dole separated carditids in two subfamilies. One, the Carditinae, and the other one, the Thecaliinae. The key character in this case is the marsupial. Thecaliinae have a marsupial, Carditinae not. But there are other classifications. These from Harris and others separate carditids based on the external sculpture, the radial ribs. Carditid with flat radial ribs are called planicostate caritids, and caritid with sharp radial ribs or tripartite or alticostate radial ribs were called alticostate caritids. But Chaban again in 1969 in the treatise on invertebrate paleontology, the seminal, the main book of invertebrate paleontology from the 20th century, divided the carditids in 7 main groups, 7 subfamilies. This one, the Carditinae, the Myodomeridinae, Venericardiini, Carditamerini, Palaeocarditinae, Carditesine, and Thecaliinae. This was the proposal followed for more than 50 years. So the carditids are divided in other two or 7 groups from different systematic point of view. With the systematic of the group, we have 28 extant genera and almost 40 extinct genera recognized within the carditids, and near to 800 species in total. This is considering the Palaeocarditinae as carditids. But we are in need of several systematic revision. From these 800 species, over than 100 are in the genus Venericardia. Over 80 are in the genus Venericor, and over 180 are in the genus Cyclocardida. So we can question, are these all wastebasket taxa? So let's leave this for now. The Carditidae have a high grade of morphological variation, including sexual dimorphisms and ontogenetic change. We already mentioned the marsupium, and there are sexual dimorphisms in other Carditidae, and we have also Carditidae with ontogenetic change across their lifespan. And let's add two more situations to see later. They have a peak in diversity during the Eocene, and their evolution was conditioned by heterochronic processes. Let's start with one of these points. And let's dive into the world of the Carditidae. Go to the phylogenetic classification. This was my main objective studying Carditidae, to study the phylogenetic relationship among the Carditidae. For attempt this objective, my work begins with the building of a new and more complete morphological matrix, morphological data for the family, including 77 species. Four of them are non-Carditidae Archiheterodonta, considered as anaerobe, the Crathatelidae and Astartidae, and 73 Carditidae species from 38 genera. At this moment, they are representing 60% of all valid genera, and more than 140 characters from the shell constitution a morphological matrix for this group, including sexual dimorphic and ontogenetic characters. Also, I include discrete and continuous characters. With this initial morphological matrix as a database, some lines of research were performed. This is a reduced sketch of these research lines and approaches. We're going to view some of them. First, I carried out different search strategies of phylogenetic research, using, for example, continuous and discrete characters, equal and implied weights for the characters. All of this research was conducted in a parsimony context, using TNG software to perform the research, perform the searches. Second, a morphological disparity analysis based on the three topologies obtained, and building phylomorph spaces. For this, I used the package Clades in the error environment, and with these metrics mentioned here. Also, I use the morphological matrix and the three topologies obtained for search the phylogenetic signal of the characters. Some group of characters show higher values of phylogenetic signal. For example, the hing character both the right and the left hinge, the right sculpture, the internal morphology, and the escutcheon. These key characters mentioned when we are talking about the Palaeocarditinae. With these different lines, the next step is to combine these multiple sources. From here, we obtain a new systematic scheme and proposed a new classification for the Carditidae. These new schemes include 7 subfamilies with the establishment of a new previously unrecognized subfamily. The previous subfamily retains are the Palaeocarditinae, the Myodomeridiinae, the Carditinae, the Thecaliinae, the Carditamerinae, but strongly reformulated, the Venericardiini, and a new subfamily previously unrecognized, the Scalaricarditinae. Also, the Planicostate and Alticostate classification was reformulated into 2 tribes, Venericorini and Venericardiini, among the Venericardiini subfamily. Also, we can recognize new suprageneric clades, the Cyclocardida with Myodomeridiinae and Scalaricarditinae, the Cardioviceta with Thecaliinae, Carditinae and Carditamerinae, and the Eucarditidae, separating the Palaeocarditinae from the remaining Carditids. Go to the next point, the systematic composition of the family. The second objective of my research was to focus on a specific group within this new scheme. First, the Palaeocarditinae and the relationship with the remaining Carditids. When the phylogenetic proposal is time calibrated, something interesting things happens. This is more visible. An important temporal gap separating the Palaeocarditines and the remaining Carditids. This temporal gap has near to 100 million years. Do you remember the phylomorph space? So some slides ago, this broad temporal gap could matches with the morphological gap seen in the phylomorph space. Let's turn the graph. The Triassic-Jurassic Palaeocarditines placed here and are morphologically distant from other Carditids from the Cretaceous research. Both gaps may be the same. As previously seen, the Palaeocarditinae have escutcheon, for example, a feature present in the outgroup in other Archiheterodonts like Crassatella or Astartida, and maybe the Palaeocarditinae are more similar to this outgroup than the Carditids. Today we have also molecular data that place the origin of the Carditidae in the Jurassic after the Palaeocarditinae. Maybe the Palaeocarditinae are a group separated, maybe a group transitional or more related to other Archiheterodonts. We don't know. We need more research in this point. go to other clade, the Cyclocardida. Specifically, we focus on the genus Cyclocardia. Cyclocardia is a excellent example of a wastebasket taxon. Cyclocardia has more than 180 species, has a long stratigraphic range, all the Carditid stratigraphic range, a wide geographic range. It is present in all continents excluding Africa, and Cyclocardia has a diagnosis based only on pleisiomorphic characters. Checking all features of a wastebasket taxa according to the definition of Plotnik and Wagner in 2006. When with the information of Cyclocardia and the new information previously showed, we perform a new phylogenetic and disparity analysis together with Luciana Giacchetti. We established a new landscape for Cyclocardia. First, we detect that Cyclocardia in Cyclocardia sensulato, in a broad sense, has more disparity values than all the remaining Carditids. They're a very disparity group. And with this new information, we split Cyclocardia in new genera and new lineages, revising the relationship with other Carditids. We provide a reduced redefinition for Cyclocardia. Cyclocardia, in a broad sense, is recognized more as a morphological rate than a monophyletic genus. Other group, the Scalaricarditinae, the new group recognized in this phylogenetic proposal. Our research allowed to recognize the early diversion representative of this group in the Eocene. This is Malarosia eos, a taxon defined by Anatoly Berezovsky some years ago from the Middle Eocene of Ukraine. And when we re-study this taxon, this research allowed to recognize a change in the sizes. We detect an interesting scenario with cases of miniaturization among Scalaricarditinae. And this scheme, the red color indicates tiny sizes in contrast to green and blue colors. All of these shadow figures are at the same scale. We detect in the Scalaricardinae and the Myodomeridae reduction in size across the time. Back to the Condylocardidae, the group previously mentioned, with what think perhaps the Condylocardidae may be a group of reduced or miniaturized Carditids, maybe belonging group as the Myodomeridae or the Scalaricardinae. Maybe the origin of the Condylocardidae is placed among these groups, and the Condylocardidae are miniaturized Carditids. We go with other group, the Thecaliinae. We already mentioned the Thecaliinae, the marsupial Carditids. So in this case, we focused in the study of the marsupial, this structure, but with a morphological point of view. In this case, we detect two marsupial morphotypes. On one hand, the external pouch. This marsupium is present in Powellina and Milneria, this type of marsupium, and the other type of marsupium is the funicular fold, this invagination in the valves. We call this structure as marsupium because the eggs and juveniles of the Carditid developed in early stages in the inner this structure. This is a real marsupium, like marsupials, mammals. We try to find the origin of this structure. A present structure in several Thecaliinae are the basal gape. This is the case of a male. The basal gape is a aperture, minimum aperture between valves when the viscus, like in muscles, is protruded. There are the Carditidae, the sister group of the Thecaliinae. All of the Carditinae has different grade of development of this basal gape in the same position of the marsupium is developed. With these distinct morphologies and a relationship between basal gape and marsupium is always present. And from here we propose an evolutionary scenario with the basal gape as an co-opted structure for a reproductive function. We can see this in living Carditis. In other group, the Carditidae, and this is an example of the bibliography. When the eggs are attached to adults, this is present in some Carditids. We imagine a scenario where the marsupium is a modified basal gape. Posterior, the incubatory chamber, the funicular fold mentioned are a refined or secondary adaptation stage for this structure. So, other group, the Venericorini, the planicostate Carditids. The planicostate were considered mainly belonging an unique genus, the genus Venericor. Other genera were proposed with some colleagues, Maxi Alvarez and Belén Santelli, using a geometric morphometric approach to assess this problem. We found several morphological differences and at least between Venericor, Megacardita from Europe, and Neovenericor from South America. Posteriorly, I recognize another planicostate genus, Eocardita, from Russia, East Russia, from the Miocene. And Venericor also were considered as an excellent guide fossil of the Eocene, because they appear in the Eocene of Gulf Coastal Plain in North America and the Eocene of Paris Basin in Europe. But in Patagonia, the story seems to be different. Previous researchers as Camacho and Fernandez considered the presence of Venericor or planicostate as a fingerprint. This word is from Conrad, as guide fossil indicating Eocene age from outcrops in Patagonia. But when I search for Pleistocene, this is the lower. This picture is from the lower valley of Chubut River in Chubut Province. These outcrops are from the Gaiman Formation, and in this outcrop we found Planicostates. But reevaluating this present the biostratigraphic potential of Venericorini in South America, in new studies we found that Neovenericor is not a Eocene taxon. This is a early Miocene taxon, and we erected a new species from the early Miocene, Neovenericor camachoi. So we go to the last group, the Venericardiini or Alticostate Carditids. This is the most diverse group within the Carditidae, and because this they had multiple species. First, we don't know when this group arose. So far, the earliest known are in the Maastrichtian Daanian around the KPG boundary, around this red extinction event. But we have this little guy, Cyclocardida, from the Aptian of Lebanon. When we are establishing Cyclocardida, in particular his intriguing external sculpture, we recognize some Venericarini features, and from here this is the typical Venericarini external sculpture with a central chord and two accessory elements, the paracostal chords. We studied this external sculpture and recognized some features of them in Cyclocardida, and finding the tripartite sculpture as a key feature of the group, we can trace the origin of the structure and the group back to the early Cretaceous, and Cyclocardida seems to be one of the first Venericarini. So we can say that the Venericardinis are originated in the early Cretaceous, and the group have a diversification around the KPG. In particular, we look for Carditidae and to study the Carditidae in the Daanian outcrops of Patagonia. From there, we scraped some neglected species as Rotundicardia maloglosorum or Calelia burmeisteri. But today, one of my objectives is to continue our search for Carditidae in other sites. Currently, we are exploring outcrops of the Arroyo Verde formation in Chubut province in Patagonia, a potential early Paleocean unit, and where we already find Carditidae. Beyond this, the Venericarini are a living group today, but they are some examples, but Purpurocardia from New Zealand or Carditidae from Mediterranean Sea, but they may be a relictual component of marine bivalve faunas. Go to other question, but about their morphological variation. We know that they have multiple sources of morphological variation, some of which we have already mentioned. Sexual dimorphism between male and females denoted by a marsupial, or by difference in globosity of shells. This difference in globosity most likely are caused by internal hatching of eggs or juveniles. There was proposed that virtually all Carditidae have internal incubation of eggs and development of juveniles. We can see another examples. But the sexual dimorphism is uncommon in bivalves, but Carditidae seems to be an exception. This is the case of Darwinicardia patagonica from early Miocene of Argentina. And among these genus, these species, we have females with more globose shells and males with less globose shells. There are other sources of morphological variability, for example the ontogenetic variation. We study this in Darwinicardia patagonica, species with more quadrate or rectangular juveniles and more elongated adults, perhaps related to ecological change across the lifespan of these species. And there are more extreme cases, like this Eocene Gusensia from France, but we are studying this one today. Now, let's talk a bit about the diversity of the group over the time. I said that they have a peak in diversity during the Eocene, but for this objective, studying the morphological and specific diversity through time, we build a morphological matrix different to those used for phylogenetic purposes, a more exhaustive matrix with 162 characters and 124 species. This matrix was used for calculate disparity metrics throughout the entire biochron of the Carditidae from Cretaceous to recent. From here we build different morphospace, and we can study what happens to the group at different moments. For example, in the Cretaceous, the morphospace is very poorly occupied, but then there are a lot of disparity around the KPG boundary, and the first diversification of the group we detected that occurs in the Eocene, with high disparity values and a reduction of the morphospace for the Eocene, this brown sector. Later, in the Neogene, we did a new exploration of morphospace in the Miocene, but with no change from here. Recent morphospace, this is from the Holocene to actual times, the Carditidae seems to be a remnant of previous exploration, confirming that they are currently a relictual group of bivalves. Let's go to the last point, the heterochronics. In this case, we define some state characters as juvenile in red and other adult state characters in green. Then when we optimize these states in our phylogenetic proposals, for example, the case of the adult size, or the presence of issues, or for example the presence of lateral death, we begin to see some interesting situations. When we look this for each group, we can see situations like this. For example, the Cardiovissata. The Cardiovissata, a group of basally attached Carditidae, shows a majority of juvenile state characters. In contrast, the Venericorini, a group of infaunal burrowing Carditidae, have a majority of adult state character, more green. When we can ask ourselves if heterochronic observed patterns are linked to the mode of life. We continue working on these issues, but they are very interesting, relating ecology, mode of life, with macroevolutionary patterns observed. Well, at this point we can rewrite what we know so far about the Carditidae with this difference. This is a brief summary of the journey. I want to remark and recommend some points. In first, Carditidae shows a broad amount of issues, especially evolutionary and phylogenetic issues, so they can be considered, the Carditidae, as a good model for the study of other bivalve groups or even other animal groups. The different approaches here mentioned were taken together with subcommon objective. We have the opportunity to mix some objective and some approaches to bolster our conclusions. The basis of all approaches are solidly and carefully morphological studies of character, of morphology. And this is the first step for our studies. The phylogenetic search is only the second step, the first step posterior to a morphological studies. Here, all these objectives are assessed under a evolutionary background. Ever. This is the end of the talk. I thanks to a lot of people for this research. First, the curators and curators of the different collection. Most of these studies are reviewing and visiting collections in different parts of the world, mainly in Argentina. And so many people collaborate with this work, and we want to thank to the financial support of CONICET, Agencia, and other institutions. I am part of the Asociación Paleontológica Argentina and the Sociedad Argentina de Biología Evolutiva, and strongly recommend joining local associations for help. They maybe can help with your research. Much more research is needed, and there are not many paleontologists, many people working on fossil invertebrates comparing with other paleontological disciplines. We need more people studying invertebrates. And if you have any questions, please let me know. And for the last, I thanks a lot to the organizing committee of this Congress. Finally, I did not want to forget to mention that in Argentina, the Argentine science is in a very complicated situation, mainly due to a government that keeps reducing the budget for science, firing people, and constantly attack the science in our country from many sides. I think that North America is in a similar is preventing a similar situation in the next months. But I want to point some attention of it. Thank you very much. Let me if you have any question. Goodbye.